All right, let's get started. So can you see the screen clearly? I can change the light to be even darker if you want to highlight. Okay. So first of all, again, the reminder, our homework 3 will be due on next Friday. So if you haven't started, please start right now. We don't want to see another congestion on the next Friday's office hour. Right? Although the workload is much lighter this time, only about perception. But if you could start early, you might be able to find the questions early and seek for help early. Right? Okay, so let us continue with the support vector machines. So in the last lecture, we have explained why support vector machines are trying to maximize the margin. Right? It actually can be justified while the computational learning theory. Right? So basically, we can use, if we search over the entire family of the linear classifiers, the VC dimension is fixed. Right? There will be no chance to reduce the VC dimension and tighten your generalization error bound. So our idea is, right. So if you search over, this is the whole family of linear classifiers, right? The VC dimension is there. It's just fixed. It's D+1, where D is the number of the input features. But how do we tighten the generalization error bound? We're trying to restrict our search space into a subset of linear classifiers, right? Because reduce the members in the subset, we're still possible to decrease the VC dimension. And if we maintain the same training error level, that means we can make our generalization error estimate to be small. Right? So the problem, how do we define different subsets of linear classifiers? So here we use a very important concept called margin. So we can define like a data-dependent margin, meaning that we can define subsets of linear classifiers whose margin for the training set is less than some gamma. Right? So, and from the previous theorem, from the Vapnik, it shows that the upper bound of a margin of a subset of linear classifiers whose margin at least gamma is bounded by this guy, right? So R and D are just constant. We don't care about, but here's a gamma. Right? So that means the larger the gamma you have, the smaller the VC dimension for this small subset of linear classifiers. That directly build up connection between the margin and small subset of linear classifier and the VC dimension, right? That gives us the result, like the larger the margin you choose, the smaller or the lower the VC dimension of the corresponding linear classifier, and then you get the better the generalization error, right? Remember, this term is determined by the VC dimension, right? So that means if we could find the linear classifiers that maximize the margin, we're gonna restrict our search space into a small subset of linear classifier who has the smallest VC dimension, and then we expect to have better generalization bound. Right? So that's the whole justification. Why should we maximize the margin during the training? So I hope everybody will be able to understand this logic chain. Right? And next, we're going to talk about how do we encode this idea into the formulation of the training objective. Right? That will utilize our geometry understanding of the linear classifiers. Right? So any linear classifier can be represented by a hyperplane. Right? The hyperplane can be viewed as a classification boundary. All the points on one side are classified as positive. All the points on the other side are classified as negative. Right? This boundary is represented by this equality, where your W1x1 plus W2x2 plus B equals to 0. Okay? And the prediction is actually the sign of your prediction score. And here's one important formula we're going to use is how to compute the distance between any point and this classification boundary. right? So it's just some formula we have seen before. One important concept is that for a linear classifier, only care about the sign, not the magnitude. That means you can skew the parameters like B, W1, W2 arbitrarily, right? As long as you multiply with some arbitrary positive number, it won't change the position of this hyperplane, right? And it won't change the classification results. So this is very, very important for us to simplify the formulation of the SVM. Okay, so now let us first try to use the most straightforward way to compensate the training objective, that is maximizing the margin. Right? So according to the definition, the margin is the distance of the closest point of the training data point from the hyperplane. Right? We have the formula, right? We have the formula to compute the distance between arbitrary point and the hyperplane, which is to multiply the label yi with the prediction score, right? And divided by the norm of the weight vector, that's the distance. Of course, here we assume your product is always positive. That means your classifier can correctly predict this instance xi, right? So their product, the label and the prediction score is always non-negative. And the margin is the smallest distance. So that means to compute the margin, we're gonna do some minimization over the training data set. We're gonna go through every training example, calculate distance between this example and the hyperplane. Then we pick up the smallest distance. That's our margin. And then we want to maximize this margin with respect to the parameters weight and bias, right? So this is kind of like straightforward composition of the training objective, right? We want to maximize margin with respect to the model parameters, and to compute the margin given the model parameters W and B, we need to go over the entire training set and find out the smallest distance. So now I want to ask, what's the problem of this formulation? Or in other words, like if you are asked to implement an algorithm to fulfill this margin maximization principle, what is a possible issue? Yeah, that's a good point. Any other thought? Yeah, I would just supplement a point. First, this is a bi-level optimization problem, right? In the inner level, to compute the margin, we'll have to do the minimization, right? Go through all the training examples. In the outer level, we have to do the maximization. Maximizing problem is not an easy optimization problem. It's known to be not easy. And even worse, this is a combined continuous and discrete optimization. Right? So in the outer level, like W and B, they're continuous. That means you do some infinitesimal change. You have to recompute the margin, right? And the margin itself is computed by some discrete optimization. You have to go through every training example. Right? That actually increases the complexity of this optimization. Right? So imagine like if you want to compute the gradient of the margin with respect to this continuous W and B, how do we compute? It's not simply like you compute the distance with respect to W and B. You're computing the gradient of the minimum distance with respect to W and B. This is really analytically intractable. If you want to solve that, you have to use some implicit gradient computation technique, which we're not going to cover in your class. Right? So here's the problem, right? Like some straightforward formulation for this maximizing margin principle is simple, right? But it's very hard to optimize. Then our next step is to simplify this objective function. We don't want to carry out this max min and combine continuous and discrete optimization. How can we do that? So first of all, we observe that, we observe that to compute the margin, right, given W and B, right, given the weight and mass, right, we essentially want to minimize the numerator, right, because the weight vector is given, right, is fixed, and the denominator is fixed, right. So we're trying to find out the minimum numerator across all the training examples. So we call the numerator, namely the product between the label and your prediction score, as their functional margin, right? So later we're going to use functional margin and this numerator exchangeably, right? And then the whole distance is called geometric margin. That's reasonable because this is our original definition of distance, right? So the major difficulty in the optimization is that, okay, every time if I change WB a little bit to update the margin, I have to go over all the training set, namely doing this minimization over the functional margin, right? That's the major cost. Then the question is, how do we avoid this step? Or at least how do we reduce the cost of carrying out this minimization? To get over this issue, we're going to use this insight we have mentioned many times, but we never claim why it is useful, right? So remember, we never talk about the geometric view of linear classifiers. We emphasize that we'll only care about the sign, not the magnitude of the weight and mass, right? That means if this is the whole space of W and B, you search over the whole space of WB is actually unnecessary. Why? Because for any point, right, any WB instance here is you skew it to another point. These 2 points actually correspond to exactly the same linear classifier, right? You got some WB here. You divide WB by 10. It will be another point in this space, but they correspond to the same hyperplane. It corresponds to the same classifier. Right? Does it make sense? Right. So that means it seems unnecessary. Like, okay, we do some free search over WB. Right? We can pick up a small subset, right, of WB. Right? As long as any point, right, outside of this subset, by proper scaling, you can find out an equivalent WB inside. That means, okay, if you only search WB in this small subset, it still gives you all the possible correct solutions. Does it make sense? Okay. This is a very important point. Okay. So now we're going to pick up a subset of WB such that any point here, the functional margin, the minimum functional margin over the training set is 1. We have the freedom to scale up and down WB so that the numerator here, right, is simply 1. Right? Remember, we can do the arbitrary scaling of WB. So now, why not we just restrict, this is the whole WB space, right? Why not we just restrict our WB subspace such that the minimum of this functional margin over the training set is simply 1. Right? And someone asked, what about any other WB outside of this subset whose minimum functional margin is not 1? We can just divide this value by its minimum function value, right? So you find a corresponding point in this subset whose minimum function margin is always 1, right? Because they're scaling by some positive constant, it doesn't change the classification boundary at all. Does it make sense? So let me emphasize again, right? Because we're computing the margin, that means we need to minimize the function margin here, right? Namely the numerator, right? We need to compute the minimum function margin over all the training set, right? And it can vary, right? If we do some free search, of course, for different WB, and it's minimum value over xi, yi, so can vary, right? So now I'm gonna restrict WB or constrain WB into subspace such that for any WB inside this subset, whose minimum of the function margin is simply 1. Okay. And we just try to search optimal WB inside this small subset. That's the key idea. But why doing this is feasible, right? Because for any WB outside of this range, right, we can find a proper skew, say by multiplying or dividing some positive constant number, you can find an equivalent point inside this range, so to give exactly the same classification results. Any questions so far? Right. What's the benefit of doing this? Oh, by the way, before we proceed, I do want to ask if anyone feels uncomfortable with at this step, because it's really, really important. Okay, so what's the benefit? If we restrict our search space into this subset of WB, that means for any candidate WB here, right, its minimum function margin is always 1. That means your margin is always 1 over norm of W, right? You don't need to conduct explicit minimization in the second second level, right? Then the maximizing the margin is equivalent to maximizing 1 over normal W. You get rid of the discrete optimization step. But of course, there's no free lunch. That means you have to put additional constraint or WB, right? You need to restrict your WB space to be a small subset space whose maximum margin, minimum margin is 1. Right? So maximizing 1 over norm of W essentially is to minimizing the square norm. Right? So here comes our formal formulation. Right? The objective function is simply to minimize the norm of W, square norm of W, which is W transpose W. Right? We put a constant half here. Essentially, is to it's like when we do the least square regression, right? We put half here. When we compute the gradient, you can get the constant 2 canceled out. So actually, just some kind of sugar, rotational sugar, right? And then we put, this is equivalent to maximizing the margin, right? And then we put a set of constraints, right, to constrain our search of WB over a small subset, right? In this small subset of WB, where the minimum function margin is 1, right? How do we put this constraint? That means for every training example I, we have this function margin at least 1, right? That means this minimum function will be 1. So now we have composite our first learning objective function for the SVM, which is called hard SVM. I will look at how to solve this optimization later, but before we go on, any questions so far? Mhm.
The D would increase, say, multiply. I understand like multiply the weights, both weights by
Mhm.
the angle.
Mhm.
Multiply by, but
Mhm.
I thought that would change.
No, it doesn't change. Yeah, it doesn't change. So because the cosmic boundary is you can take a look at our algebraic form of the cosmic boundary. It's something like that, right? It's an equation. That means you multiply WB by the same positive constant, doesn't change at all. Yeah. But of course, you have to multiply by positive constant. If you multiply by negative constant, you actually change the direction. You flip the sign. Right? Yeah. Any other question? Okay, great. So so this is the hard SVM formulation. So first of all, the benefit is that, okay, by introducing a set of constraints, that means we reduce our search space into a smaller subset. We kind of eliminate some more complex and costly discrete optimization to compute gamma, right? The margin in the inner level, which will make our life easier. But that does not necessarily mean the whole optimization problem is easier to solve. Later, we'll discuss, especially when we want to extend to nonlinear classifiers, when we build kernel trick, we still need a series of steps to simplify the subjective function. But here, even for hard SVM, we're afraid it's not feasible in practice because remember our actual constraint is like that, right? We want every example whose function margin is at least 1. Right? And remember, previously we used this product, the sign of this product to indicate whether we can correctly predict this example or not. Right? If our WB can correctly predict the label of xi and yi, this product is always a non-negative, right? This is from our previous discussion. Right? And now we not only require this product is non-negative, further, we want to require this product at least 1. Right? That means you must ensure this data is linearly separable, right? Because this constraint applies to every training example. But what if the data is not linearly separable? If the data is not linearly separable, then the constraint space is just empty, right? And if you do constraint optimization, if your feasible region is empty, that means you have no solution. In practice, we have to assume that there could be many cases that your data is not linearly separable. So looks like the hard SVM help us to address part of the problem, but still not practically useful enough. So how can we address that problem? In practice, in order to deal with non-separable data, non-linearly separable data, right, we have to compromise on the property of data. Namely that we assume, okay, maybe there are some outliers. If we could find out and exclude these outliers, like these black points here, then for the remaining points, they are linearly separable. Then we want to adjust our formulation to give some flexibility such that we can identify and exclude some outliers. Okay? Then we want to maximize the margin for the remaining training examples, which are linearly separable. That's the idea of the soft SVM. So why this is reasonable, right? If you look at the generalization error bound, right? If you can just exclude a small number of the examples as outliers, right? We can allow those examples to break into our margin. That means we might suffer from a little bit larger training error, right? But at the same time, because for the remaining training examples where they are linearly separable, we can still want to maximize the margin. For that, we have a smaller VC dimension. So we can make this bounding term to be smaller. So overall, we expect that we have a better trade-off of those whole summation so that we can get a smaller generalization error bound. That's the idea. Okay, then the problem is okay, then the problem is how do we formulate? How do we give some mathematical formulation and to allow us to identify which outliers should be picked up and throughout, and then we just look for the maximum margin for the remaining examples. Right? So for every example, we're going to introduce a slack variable Ci. Okay. And then we modify the hard SVM constraint as follows. Right? So first, we require the slack variable to be non-negative. And then we require that the functional margin is just no less than 1 minus Ci. Right? And actually, the value of this Ci gives us the flexibility to break into the margin. If Ci is 0, what does that mean? Yes, the high SVM, right? If Ci is 0, that means your function margin is no less than 1. It is consistent with the hard SVM constraint. That means, okay, this particular point, xi, yi, must stay on the margin or outside margin, right? If Ci is absolutely bigger than 0, then xi, yi could break into the margin, right? Because the constraint becomes, okay, the function margin is bigger than some value less than 1. So now, by applying these modified constraints and additional slack variables into our formulation, we come out our soft SVM formulation. Okay. So for every training example I, we have a slack variable, non-negative slack variable, namely Ci non-negative, and then the function margin is no less than 1 minus Ci. Then in the training objective, okay, we have this half square norm, which is equivalent to maximizing its inverse, right? And then we plus another term, which is summation of all the slack variables. And C is a hyperparameter, it's a constant, positive constant. So first of all, the constraint comes from, the constraint modification directly comes from the hard SVM, right? But what about the objective function? Right? So notice that we not only modify the constraint, right? We also modify the objective. The hard SVM objective is simply to minimize half of the square norm of the weight vector. Right? But in soft SVM, we plus an addition term. Right? We want to, this is a maximized margin, right? We want to minimize the summation of all the slack variables. Right? Every example has a slack variable. Why do we want to minimize the summation of slack variables? Yeah, but why do we want to do that? Can you say it again? Yes, exactly, right? So to see why, right? Let us consider what if we get rid of this term, right? If we just modify the constraints in this way, right? That means for every example, we have some free slack, non-negative slack variable. You can allow it to break into margin or not, right? And we only maximize margin. What will happen? Yeah. So I can just let me just random draw some example, right? So suppose this is your positive examples, this is your negative examples. Right? So if in our objective function, we never consider the effect of slack variables, we just consider, okay, we want to maximum margin. And we have the freedom to exclude whatever examples from your training set, right? That means to maximize margin solely, I can try to exclude all the other examples, right? All those examples. I'll only preserve two furthest point in your training set. And I look for a linear classifier who has the largest margin for only 2 points. Of course, I get my margin largest, right? But what's the consequence? The consequence is that, okay, if you allow all those examples to break into a margin, your training error can increase significantly, right? And remember, our true error is upper bounded by training error plus some term regarding the VC dimension, right? So that means it's a trade-off between the training error and the VC dimension. It's not solely dependent on the VC dimension, right? You trying to minimize the VC dimension, that means you have a maximized margin. Of course, you can make this term to be as small as possible. But if in the meantime, you drastically increase the training error, now overall, the generalization error estimate is still not good. Right? That's why in our objective formulation, we still need to account for the summation of the slack variables. Right? In the ideal case, I will say is the ideal case, but consider that if all your Ci here is 0, that means all the examples are used and to look for the margin, right? All the examples are not allowed to break into the margin. Right? They must stay on outside margin. That's one extreme case, right? The other extreme case that is all Ci is non-negative, right? It's bigger than 0. That means all the example can be excluded. Right? So you need to find out the best trade-off between the two extreme cases. Right? That's why we need to consider both cases, right? One is to maximize margin, the other is to Yeah, you're right. Because the example I draw here is pretty simple. Like if I draw a example here, draw a line here, well, you can see, okay, I still get 0 training error. But what if the examples, the cases are much more complex?
Apply the point onto the equation of the separating algorithm. As long as it's positive or negative, you still be classifying it as the non-neutral, even if it's inside the margin.
Yeah, you got a chance to still correctly classify the examples, even if break into the margin. But as long as the examples break into the margin, you have a higher chance to wrongly predict it. That also includes the training exam. So here, probably I draw the examples a little bit too easy. Like you can imagine, you have a positive, negative, negative, positive, positive, negative, negative, right? And you got positive, negative, right? If you pick up this one, right? You draw a line here, you still got a lot of examples to be misclassified. I'm not saying, okay, if your examples break into margin, it must all wrongly classified. It's not that case, but it can indeed increase the training error significantly. And we want our flexibility to tune that. Like you want as many examples to be excluded so that you can max margin. But at the same time, you don't want to, because of breaking into this margin, you don't want to the increase of the training error to be too much. That's why in our design of the objective function, you want some trade-off. And this trade-off actually is also reflected by this hyperparameter C. Mhm. Yeah, you can do that. I'm trying to explain the original version of SVM, but I guess there will be like 10,000 papers or 20,000 papers. They're all playing all kinds of trick to make this easier. Too many papers about that. Mhm. Yeah, there will be one Slack variable for one training example. Suppose you have 100 training examples, you have 100 Slack variables. Why? Because we need the flexibility, right? Any example might be on the margin or might break into the margin. We need sufficient flexibility. Then during the optimization, we can automatically determine which examples should break into margin, which example should be on the margin or stay away from the margin. Other question? Okay. So yeah, the trade-off between the two terms is reflected by the hyperparameter C here. And again, you have to tune this hyperparameter for different applications. Right? So now, given this soft SVM formulation, right, how do we minimize that? Right? So although we only have like one level optimization, but those constraints are not easy. Right? So we're gonna first explain one simple way of doing that. That is, we want to eliminate the Slack variables. Right? How do we eliminate? So if we look at, for every training example, I, right, we have the corresponding Slack variable Ci must be non-active and must be no less than 1 minus the function margin. Right? So we know that Ci must be no less than the maximum of these two. Right? You need to satisfy both constraints simultaneously. That means you must be no less than the maximum of these two lower bounds. And then if you look at the training objective function, right, this is a maximize margin, which is solely term regarding W, right? This term is to minimize summation Ci. So why not we just choose the minimum value Ci can choose. Right? So in this way, we can just replace Ci by the minimum value it can use. Right? That means we can reduce the training objective into the following form. Right? Because Ci is at least 0 or at least 1 minus this function margin, which is directly derived from here. Right? So we know that minimum value Ci can choose is just the maximum value between 0 and 1 minus function margin. Right? So because our objective is minimize that, we just pick up Ci to be the minimum value it can choose. So in this way, we actually eliminate all the constraints. And also we limit this additional variables Ci's. And then we can apply kind of standard optimization approaches like gradient descent, stochastic gradient descent, which we're going to discuss in the next step. Right? But before we proceed to the algorithm steps, let us take a closer look at this simplified form. Right? This form actually is more interpretable and can give us more general knowledge about how to composite a machine learning objective function. Right? So we can see that after this simplification, we have two terms in our objective function. Right? The first term is half of the square norm of the weight vector, which the implication is that we try to maximize margin. And what does the second term mean? Yeah, I mean, as the name suggested, right? It's a penalty for the prediction, but why does it penalize your prediction? Yeah, if we make a contrast to the least mean square training or regression problem we discussed previously, right? So when we composite the training objective function, we go over all the training examples, right? For every training example, I use my current model to make prediction and look at the difference between the ground truth and their prediction. And this difference is viewed as some kind of penalty or cost, right? So this actually gives another form of the cost, right? And we can do some kind of analysis, right? Case by case. We actually have 3 cases. Right? First, if this example is correctly classified, that means the function margin is non-negative, right? And also it is outside margin. That means the function margin is bigger or equal to 1, right? Then 1 minus the function margin will be negative. Then this maximum will give 0. That means you have 0 penalty or you have 0 cost. Another case that if the example is incorrectly predicted, like if the example is incorrectly predicted, we know that this product is is less than 0, right? If less than 0, 1 minus some negative value will be positive, right? So the max between 0 and some positive number is still positive. That means you got a positive penalty, a positive cost, right? Which is 1 minus the function margin, right? But the interesting observation for this penalty is that even your example is correctly classified, but if it is within margin, you still have some penalty. So within margin, that means, okay, this guy is less than 1, right? Although when it is correctly predicted, that means the value here is non-negative. But 1 minus something less than 1 will be positive. That means you still have some positive penalty. So this particular type of loss or penalty is called hinge loss. It's SVM specific. As we discussed before, right? You can come up whatever loss function you like. Right? You want to penalize you want to penalize the wrong predictions. You want to give a word to the correct predictions, right? And SVM, when you do, all kinds of simplification, merging analysis, you end up with this so-called hinge loss function, right? The interesting property of hinge loss is that even you can correctly classify the example, if that example, if your boundary, if your clustering boundary is too close to that point, you can still get some kind of penalty. Right? So there's some kind of interesting observation between the relationship of hinge loss and the 0-1 loss. Right? So we know that in ideal case, for the binary classification problem, we could use like 0-1 loss. That means, okay, if you make correct prediction, you get 0 cost. Okay? That means your prediction score is and your prediction score multiply your label is non-negative, you get 0 loss. But if in wrong prediction, you get 1 loss. And here is the curve of the hinge loss. So actually, hinge loss is an upper bound of the 0-1 loss. Okay? So some in the computational learning theory, people are interested in developing some kind of upper bound of the 0-1 loss. They will like 0-1 loss as some kind of golden standard, but it's very hard to optimize. So you want to develop some kind of surrogates. And if you want to manage something, the surrogate is better to be some upper bound. Right? So the interesting observation, let me emphasize here again, right? If your classification boundary is distant away from the point you correctly classified, right? It's further away, then you got 0 penalty, right? And if it is wrongly classified, well, you get some penalty, right? But in this grace area, like even you correctly make the prediction, but if the clustering boundary is too close to the point, you still get some penalty. So that means the training is encourage you to find your classifier to be as far from the points as possible. Okay, so any questions so far? Okay. So later we will discuss other models, loss function like logistic loss. You will see we actually can construct a zoo of loss functions, different curves of loss functions, and give you different insight, and also show their relationship with the zero loss. Okay. In summary, the hinge loss gave us the three cases. First, if the example is correctly classified and is outside margin, that means the example is far away from your clustering boundary, you don't have any penalty. If your example is incorrectly classified, the penalty will be 1 minus your score. That means the larger skew the score you have, actually the larger penalty you have. Right? That reflects the degree of the mistake you have made. Right? And the interesting area is that, okay, if you correctly classify example, but still is too close to the clustering boundary, you still have to bear some penalty. Right? So from the structure of our loss function, right, we can make some comparison with our previous loss function use. Right? In our previous discussion, like in least mean square problem, or in a perceptron problem, our loss essentially is to define over the trained data. Right? That means we want our training error to be as small as possible. Remember, in the square loss, it's just a square loss over the entire training set, or the perception. Although it is an online learning algorithm, but it only look at if you can correctly predict every training example. As long as you make mistake, you update the model. Right? So we define if your learning is to find a hypothesis that has the lowest loss on the training data, this principle is called a risk minimization. Okay? So basically, you can come up with whatever loss, which evaluate how good your classifier performs on training set only. And you just minimize the loss to find your optimal classifier. So if you follow this procedure to construct your learning model, this is called risk minimization. Obviously, this is different from the SVM loss. So the SVM loss, if we have if we look at here, right, in addition to the hinge loss over the training set, we have an additional term. Right? This additional term in the SVM context is to maximize margin. But in general, why do we maximize margin? We want to minimize the VC dimension. Right? The VC dimension indicates the expressivity or complexity of your hypothesis space. So actually, this additional term can be viewed as a regularizer. Right? Want to penalize overcomplicated hypothesis space. If in your training objective formulation, right, in addition to some loss on training data, you add some kind of regularizer which penalize the complexity of your hypothesis space, then you try to minimize the whole regularized loss function. This is called a regularized risk minimization. So in general, in our training objective function, we define a regularization function that penalizes over complex hypothesis. Right? This is a capacity control. And also we define a notion of loss over the training data, right, to evaluate how good your hypothesis performs on the training data. Right? Then the learning is to find a hypothesis that has the lowest regularizer plus training loss. So if you follow this procedure, it's called regularized risk minimization. And this one is actually the dominant choice in the machine learning practice, right? Especially nowadays in the neural network area, right? It's very easy to like use 100 layers neural networks, millions of parameters. Right? They're very, very complicated. That means their VC dimension can be very large, right? Then you have to regularize. You have to regularize the complexity. You have to penalize the overcomplicated neural networks to find out appropriate one to fit data. In this way, you can get the best generation error rather than just, okay, I try to find out a large neural network, like as deep as possible, as wide as possible to give zero training error. Okay, any questions so far? Is everyone comfortable? And there's one hyperparameter we want to emphasize again, right? Which is a trade-off between the regularizer and the loss function, right? And this one, actually, there's no like ground truth value, right? You have to choose them according to a particular application. In some application, 0.1 might be good. In other applications, would be 1.0, 1.5. So it's totally application dependent. Okay, so we have finished the objective formulation of SVM. Okay? Next, we're going to talk about how do we optimize those objective functions to find out the optimal WB to give our linear classifier. Right? So we're going to introduce, there are a lot of ways to optimize the objective function. Sorry, let me first hide the floating panels. So it's really annoying. Okay. So here we're going to introduce a very commonly used and very simple framework. It's called stochastic gradient descent. Right? So we have explained how we use SGD to train the linear regression problem. Right now we're going to have some revisit, but have a more in-depth discussion about that. Right? So this is SVM objective function. I'm not going to repeat again. Right? So the outline of this piece of topic is as follows. Right? We're going to first give a review of the convex function definition and the gradient descent framework, which actually we discussed previously, right? And then we review the stochastic gradient descent framework. Then we're going to discuss what's the pros or cons about gradient descent and stochastic gradient descent, and when should we use gradient descent, when should we use stochastic gradient descent. And later we'll talk about the issue of hinge loss. Actually, you cannot directly use the stochastic gradient descent because the hinge loss is not differentiable. We have to get around this issue, right? So then we'll introduce the ideas called the concept called subduality or subgradient. Right? You see that as long as you can find subgradient, even this function is not differentiable, you can use subgradient instead of gradient to perform gradient descent or stochastic gradient descent, and all the results and guarantees are there. Right? Then we'll talk about stochastic subgradient descent for support vector machines. And finally, we'll circle back to the perceptual algorithm we discussed previously. So although the learning or updating rule of perceptron is quite heuristic, you find that you can understand it as a way to do stochastic subgradient for some objective function. Okay, so first let us take a look at the convex function and gradient descent. Right? So first of all, here's the conclusion. Right? The SVM objective function here is convex in the weight vector NB. Right? The reason is simple. This is projective function. Right? Everyone has practiced in your homework 0. You have shown now this is convex. And this guy is convex as well. It's pretty straightforward to show that by definition. So that means in principle, you can use any convex optimization technique to minimize SVM objective function. And for convenience, we will use the notation of sugar we introduced in the linear classifier, right? So we're going to fold the bias parameter B into W, right? And correspondingly, we augment each feature vector with constant 1, so that this B value corresponds to the constant feature value 1, right? So that we don't need to explicitly write out the bias parameter B here. And we denote the original weight vector, I mean, no B is included by W0. So here is our simplified objective function form, right? Half W0 transpose W0. W0 does not contain any bias parameter B. And plus this hinge loss, right? So the function margin is simply Yi W transpose Xi, because the bias parameter has been folded into W, right? We have a constant feature, a constant 1 added into Xi. Right? So remember the definition of convex functions, right? When we say a function f is convex, if for every input in the domain, say u and v, and for every positive value of lambda between 0 and 1, we'll have that if we first do the convex combination of u and v in terms of lambda, that means we first combine the inputs, then evaluate. This function value will be less than or equal to the convex combination of the function values and u and v. That's the definition, right? And we have mentioned that some property of the convex function, right? If this convex function is differentiable, that means at any input x, right, fx will be lower bounded by this linear function. So u is a variable, right? X is fixed. So this just means f of u plus the gradient of your function f at u dot product with x minus u. So what does this mean? This is a tangent line, right? Yeah, this is a tangent line, right? Here, right? Suppose this place is where u locate, right? And the gradient of f at u is actually the slope of this tangent line, right? And it passes through u and fu, right? So this is actually a tangent line. So this result tells us that if the function is convex and is differentiable, then every tangent line or tangent plane will lie below the entire function body. That's the geometry view of convex functions. Right? Does it make sense? Right. This is very important for us to explain what does it mean for subderivatives or subgradient. So here are like instances of common functions, like linear functions are convex, and quadratic functions are convex, and max function are convex. However, max function is not differentiable. I will later see it, right? And this is some like two-dimensional function, right? This cone is a convex function as well, right? So how do we show a function is convex? We can first using the definition, right, to show that convex inequality applies for every possible inputs in the domain, right? Or if the function is differentiable, twice differentiable, right? Then we can show that the second derivative is non-negative, right? If this function is a vector function, then you need to show the Hessian matrix is positive semi-definite, right? Or you can show, if this is differentiable, you can show this inequality holds. So there are several commonly used ways to show a function is convex. If in the definition of convex function, right, if we change the direction of your inequality, like I require the function value evaluated at the convex combination of inputs is bigger than or equal to the convex combination of function values, then this type of function is called concave functions. You can view it as a mirror family of convex functions. But here I want to emphasize that convex and concave functions are a really tiny subset of all possible functions. In practice, most functions are not convex nor concave. There are many functions that are neither convex nor concave, like this guy and this guy. They're not convex nor concave. Right? But we can see that locally they might be convex, they might be concave. Right? Those are very important in optimization theory, right? Especially if you want to show some convergence, local minimum convergence. Okay, so in general, if you want to do optimization, like if your function is continuous, is a differentiable, if you want to maximize function, you want to minimize the function, we know that if we find out, say, maximum or minimum, we know that the gradient must be 0, right? But this is just a necessary condition. That means if your differentiable function, if your function is differentiable, if you find some point which is optimal of that function, then the gradient at that point must be 0. Right? But can we say if the gradient is 0, then you have arrive at the minimum? Yeah, it can be maximum. It can be either not a maximum or minimum, right? So here's one example here. Right? So you can see that this point is not maximum, it's not minimum, but the gradient is still 0. So really, if people call it, okay, if you have a gradient 0, then this point is called stationary point. The stationary point is not, it could possibly neither maximum or minimum. That's in the general case. However, if you're dealing with convex function, things becomes a lot easier. Right? For convex function, so the gradient being 0 is both necessary and sufficient. And there's no like global and local minimum difference between global and local minimum. As long as you find some minimum, it will be the global minimum. So convex functions has a lot of very nice properties. That's why people, when do some kind of research, are trying to focus on a subset of elements which are nice, has a lot of guarantees. Okay, so far, any questions? Yeah, we need to keep all those in our mind, because as we proceed, we're gonna have we're gonna revisit these concepts again, right? Especially when we try to extend our support vector machines to, say, the dual space. We want to embed the kernel trick, because fortunately, all the SVM formulation is in the convex domain, so we can leverage a lot of nice properties. Right? Okay, so back to our SVM formulation, right? We know that this is a convex function in W. Here, W is augmented W, includes both the weight vector and the bias parameter, right? So this is a quadratic optimization problem, because the objective is quadratic, right? So you can use whatever convex optimization libraries of doing that, but the problem is very slow. And we notice that because this is a free optimization, there is no additional constraints, so we can simply use gradient descent. Right? So let us look at the gradient descent framework. Right? We have seen this before, right? So given the objective here, right, we can start with some initial guess of our parameters, WC, W0. Then we do the following iterations until convergence or some kind of stopping criterion are met. Right? At each step, we compute the gradient of the objective function at current model parameters. Then we update our model parameters by taking the step in the opposite direction of the gradient. Right? This is called gradient descent. Why do we take an opposite direction of the gradient? Yeah, because we want to minimize, right? And gradient is direction to increase the function. If you want to minimize the function, we need to follow the opposite direction of the gradient. Right? So this is some example, right? We start from W0, and the gradient direction is toward the right. So we move toward the left, right? So get W1, we'll keep doing that. We'll get W2, keep doing that until convergence, or it is close enough to some minimum. Right? So now let us try to apply this framework for our SVM. Right? This is our SVM objective function. We initialize our model parameters. Then in each iteration, we'll compute the gradient at the current model parameters. We denote it by this gradient, right? Then we update our model parameters using gradient descent. Here, we introduce a positive constant R, which is called learning rate. So this looks straightforward, right? But what's the problem? Yeah, I mean, that's the next question we're gonna address, right? But before that, what is the disadvantage of gradient descent in nature? Efficiency in update, right? We discussed it previously, right? So we know that the training objective function, right, is really some kind of loss term over all the training examples. Even if you're able to compute the gradient of this objective function, that means you have to go over every training example, compute the gradient of that loss term on that training example, right? That might be okay for a relatively small set of training example, right? But nowadays, like if you have a very, very large number of training examples, like you have 1 billion training examples, right? That means to compute one gradient, you have to go over the 1 billion examples once. Right? And of course, really, we need at least hundreds of updates to converge. Right? So that means you have to go over this 1 billion examples like hundreds of times. That is really, really inefficient in updating the model. This kind of reasoning also applies to the least mean square regression problem. Right? That motivates us to use a much more efficient updating scheme, which is called the stochastic gradient descent. Right? So what is stochastic gradient descent? Could anyone? Yeah, exactly, right? So the stochastic gradient descent is not like, okay, for gradient descent, I'm gonna go over all the training examples to accumulate the loss gradient, right? Add them together to get the exact gradient. Stochastic gradient descent, like they just go over one example or just every few examples, then they accumulate the gradient. They get some like a very rough approximation to the gradient. They use that gradient to perform the gradient descent update. Right? So imagine that you have 1 million examples or 1 billion examples. You get stochastic gradient after you go through every example. Right? If you go through a whole training set, that means you update the model for 1 billion times. So your updating efficiency will be much, much higher. Right? This is something we have discussed before. Right? Of course, every update might be low quality because the gradient you used is just an approximation. Right? But as long as in enough large data, you have a much more frequent update than gradient descent. So in many, many large data applications, stochastic gradient descent can still give you a high quality model learning procedure, and which is much more efficient than gradient descent. Okay. So the problem of gradient descent is that, okay, it requires summing over the entire training set, right? Slow, so it does not really scale. So we want to switch to the stochastic gradient descent framework we used before. So we initialize our weight vector, say by 0. Then we go through, say, big T epochs. Each epoch meaning you're gonna pass through the whole data set once, right? And inside each epoch, you're gonna first random pick up an example from the training set. Then you duplicate this example. Like suppose you have n training examples, right? Then you duplicate this example for n times. You pretend this example as the whole data set. Then you compute your SVM objective at the current weight parameter and the current faked data set. Right? This is your faked training objective function, right? Then you compute the gradient. Then you update the model parameters according to the gradient descent. Right? So here, n, as we just mentioned, is the number of training examples. And once you update your W according to this gradient computed by this faked objective, we call this a stochastic gradient, right? You move to the next step where you randomly pick up another example, right? And you repeat this example to fake the data set again and compute the gradient, which is approximation or stochastic estimate gradient, and update W again. You do it again until you finish looking at the whole data set. You finish one epoch, you do it again until you finish all epochs, and you finally return your model parameters, estimate model parameters. Any questions so far? You can use sample with replacement or without replacement. Doesn't matter. Yeah. Oh, C is a hyperparameter. As we mentioned that in SVM formulation, right? You got two terms. One is the regularization term. The other one is the hinge loss term, right? You have some hyperparameter C to make a trade-off. So is everyone okay with this framework? I think it's just a application of SGD framework we discussed before. Okay, so here I want to explain a little bit the general framework of stochastic gradient descent. A little bit math intensive, but it's not required for you guys to prove anything. But I just want to give you a formal definition of that. Okay, so in general, if your objective function is of the following form, W is the model parameters, right? RW is some kind of regularization term, right? And L is some kind of loss term. L, X, and W means that the loss applies to n training example, right? You're going to go over all the n training examples to compute the loss accumulated over the whole training set, right? And how does the stochastic gradient descent work, right? And why is stochastic gradient descent, in theory, can guarantee some kind of convergence? Right? This is derived as follows. So first, we can manipulate this term. Right? We can introduce a factor n. N is number of training examples in total, right? Inside the summation. And outside, I just multiply 1 over n. So this is reasonable, right? Because n and 1 over n just cancel, right? But what's the benefit of adding these two additional constant factors, right? We can view it as some expectation of a random objective function, right? How do we see that, right? We can consider a categorical random variable, right? K, where the range of K is 1, 2, 3, 4, 5, 6 until n, right? This is like rolling a dice, right? But you have n points in the dice, right? And the chance you pick up K to be any value between 1 and n is just 1 over n. That means uniform distribution, right? So then this form is equivalent to adding the regularization term plus some expectation over n times this loss function, where the input to the loss function is xk. Right? Remember, k is a random variable, right? K index, which particular training example you selected, right? So xk itself is a random variable. You take expectation with respect to k, that means just instantiate all different possible choice of k and multiply with probability, which gives you this. Okay. And of course, R of W, is constant to K. That means you can just move this regularization term inside the expectation. So then you can rewrite your objective function as an expectation of this guy, right? RW plus say times big N times the loss at xk. So what's the benefit of this? If we want to compute the exact gradient, right? That means you take the gradient over f. That means take gradient over the expectation, right? In many cases, we can exchange the expectation and the gradient. So that means we can move the gradient inside the expectation. That means, okay, I can first randomly pick up a k. I compute the loss on example xk, right? I duplicate for n times, and then times c, and plus the regularization term, and then I take gradient. And this guy, inside the whole expectation, is still a random variable, right? Because it is indexed by k, right? K is a random variable. So we call the gradient inside expectation as a stochastic gradient. Stochastic means random, because it's random variable, right? And we know that if we take expectation over this stochastic gradient, we recover the exact gradient. This stochastic gradient descent this stochastic gradient is called unbiased stochastic gradient. And the current theory can show that as long as you use unbiased stochastic gradient to update the model parameters with proper scheduling of the learning rate, it will converge to some local optimum with probability 1, almost surely. I'm not going to talk about what does it mean for almost surely or with probability 1, but you can basically we will like, okay, I can almost always converge to the local optimum. Right? That's why in the previous framework we just mentioned, right? Every time we need to randomly pick up an example and duplicate for big N times, right? To fit a data set of the same size of the original training data set, then plus the regularization term, and use that objective function to compute the gradient. Because our goal is to compute an unbiased stochastic gradient. Right? And only when we use unbiased stochastic gradient to update our model, the convergence can be guaranteed. Okay, this is kind of like a theoretical, very brief theoretical introduction about why we're gonna compute the stochastic gradient descent in this way. And actually, the basis for almost all the current stochastic gradient descent algorithm used in practice. Right? But again, you don't need to memorize all this, and we won't test you if you understand if you can recite this. But we do request you to look over this procedure and know why we compute the stochastic gradient in this way. The reason is simply because we want to obtain unbiased stochastic gradient. Unbiased means if I take expectation, I can recover exact gradient. In that case, there's a bunch of theory. By using series analysis, you can show it can converge to the local optimum almost surely. Okay, let's stop here today. See you on next week.